Okay. Anybody come up with any less efficient but more algebraic ways of doing this?
Yeah, I just found the inverse and then...
Okay, cool. That's pretty much what I'm thinking I need to do, but I'm wondering if there's an interesting trick here, because what's playing in my mind, and I haven't done this question yet, is I can certainly find A inverse generally. That'll be in terms of P, and it's probably going to have a quadratic version of P as my denominator, which is going to be annoying. And then once I've found A inverse, I can find the determinant of A inverse. Again, it will be in terms of P, and I can probably solve that. So that will probably work. But I know that the inverse of A inverse is just A. We talked about that yesterday. So then I'm thinking, well, the determinant of A inverse would be the denominator of the rearrangement of A inverse into A to get the inverse. So I'm wondering, like when you said earlier, Max, 1 or negative 1, part of me sort of thought, I feel like it has to be 1 or negative 1 because there's no fractions in there. But let's see how we go.
It's actually negative 0.618. Oh, 1 minus root 5 over 2 or 1 plus root 5.
Oh, so that's the golden golden ratio.
Yes, it is.
You got that as well? Yeah. Okay, all right, let's see where we go. So A is this, which means that the determinant of A is equal to 1 times P minus 1 times P squared, which is P minus P squared. That's a B. And so therefore, A inverse is equal to P over P minus P squared, and then negative 1 over P minus P squared. And I wonder if there might be another way we could do this. I'll have a look at it in a second. But here I get negative P squared over P minus P squared, and then here I get 1 over P minus P squared. Firstly, I can simplify the first two. I'm hesitant to do it because it might actually mean I have to equate the denominators later on if I'm adding fractions. So right now I'm thinking I probably won't simplify the first two. But I'm wondering as well whether if I leave A inverse, because the question's not finished, as 1 over P minus P squared of P negative 1 negative P squared 1, whether that might also be an easier way of doing it. But let's...
P divided by P, P plus 1 divided by P plus P to the power of 3.
Are you talking about what I'm on at the moment?
Yeah, I think so, the way you did it.
But are you on this step, or are you talking about future?
Yeah, future.
Can I get to the future first? Yeah. Is that all right? Now I'm going to get my determinant of A inverse. And my determinant of A inverse is P over P minus P squared times by 1 over P minus P squared. And then I have to subtract from that negative 1 over P minus P squared times negative P squared over P minus P squared. So this has worked out nicely because my denominator is going to stay the same. But actually, had I simplified these first two, my denominators would also stay the same. So I'm expecting here I'll be able to do some cancelling at some point as well. But I'm just going to carry on with it like this. I get P over P squared minus P, and that's all squared. And this, subtracting P squared over P minus P squared, squared. And that works out quite nicely because P minus P squared over P... Oh, sorry, that shouldn't be squared. That should be squared.
So I was wrong. Don't worry about it.
Sorry?
I found the determinant of A.
Oh, okay. So I get P minus P squared on the bottom there, squared. One of those cancels with one of those, leaving me with 1 over P minus P squared. And I need that to be equal to negative 1. That's what the question's asking. So now I'm going to add a bit more space and just keep this vertical. So that gives me, obviously, if that's equal to negative 1, so I'll put negative 1 here, I get negative P plus P squared equals 1, which gives me P squared minus P minus 1 equals 0, which might still give us the same thing. That might still be the golden ratio. Maybe it's the golden ratio both ways because that's what's special about the golden ratio. P will be equal to, I kind of expect you to be able to solve quadratics. So I'm going to run through and just do the quadratic formula, yep.
Why did we do all of that when we could have just taken it into AD minus BC and then rearranged?
Does that mean the determinant of A inverse is the same as the determinant of A?
Yep, in this case. I don't know what you mean, James, sorry.
From
We could
A.
have just put put it as -1 equals P minus P squared to start and then.
But the question says show that find the value of P such that the determinant of A inverse equals -1, and I don't know A inverse. I know A. So when I first find the determinant, that's the determinant of A, not A inverse.
Okay.
So it does still work. It works out, and I think it's just the design of the matrix. Maybe it works out otherwise, but I believe it's just the design of the matrix. Anyway, I get -1 plus or minus the square root of B squared, which is -1 squared, minus 4 times 1 times -1, all over 2 times 1, and that gives me 1 plus or minus the square root of 5 over 2, and that is indeed the golden ratio. So P has to be that, either that 1 plus the square root of 5 over 2 or 1 minus the square root of 5 over 2 for that to work, going through that way. There might be quicker ways. I kind of suspect that had I left it like this, I could have then worked out the determinant of A minus as just that thing multiplied by the determinant inside. It might have worked. Yeah, maybe. I'm not sure. But either way, this is the technical way of doing it. It's quite algebraic, but it's very doable. Simplifies nicely. We get to there. If it was a tech active exam, you could certainly rely on technology, but that could come up in a tech free exam as a complex question. Complex familiar now. Any questions on that?